Okay, let's look at an example of a child playing on a swing. All right. So we have a child on a swing in a playground. All right. And what do we know about this problem? Well, we know that at the lowest point of the swing, the lowest the low is 4.9 meters per second. This is given to us. So this is the speed at the lowest point of the swing, and we want to find how high she will go from there. All right. So let's visualize this situation by drawing a simple diagram. We have the child swinging. Let's say this circle is the child. Children are not circular, but in physics we are ignorant. And let's say she is swinging. All right. That's her final position, and we want to find how high is this from her original position. Let's say this is her original position. Maybe it's a little off, but it'll have to do. Let's call this y equals 0. Alright, this is y equals 0, and this is this height. Let's call it h. Alright. Okay, so this is the final position. This is final and this is initial. And we know in the final position we want to find height. We want to find this y coordinate, alright, or the y displacement. And in the initial position, what do we know? We know that initially the velocity at the lowest point was 4.9 meters per second. Cool. Now your original instinct would be to go ahead and use Newton's second law, because we know that this is a rope tied to the swing. So the rope must be exerting a tension force, and so we could in principle apply Newton's second law of motion. However, we have to realize that the tension in this string holding up the swing is constantly changing as the child swings back and forth. So for a changing force causes a changing acceleration, and we know that changing acceleration, for our kinematics, it is not valid. Our kinematics only work when acceleration is constant. So we cannot use kinematics or Newton's second law to solve this problem. But in physics, will often have different principles to solve the same problem. Here, we are going to try work energy theorem. Why are we trying work energy theorem? Well, because we are trying to find a position, and we know that we know energy quantity that is known as potential energy, which is an energy based on position. So if you're looking to find position in this kind of scenario, well, often you can use the energy work theorem, because of the fact that we have defined an energy both for motion, which is kinetic energy, and based on position, which is potential energy. Let's go ahead and write down what our work energy theorem tells us. It tells us Ki plus Ui, U is potential energy, K is kinetic energy, plus the work done by non-conservative forces is equal to Kf plus Uf. So the initial kinetic energy plus the initial potential energy plus the non-conservative work, which is the work done by friction or air resistance, is equal to the final kinetic energy plus the final potential energy. In this problem, we are ignoring air resistance, and since the swing is not touching the ground, we can ignore friction as well. So the work done by non-conservative forces is 0. The summation of kinetic and potential energies, this has a name. Let's use a different color for that. Let's use red, and this is named as mechanical energy. The summation of kinetic and potential energies is called mechanical energy. So the fact that initial mechanical energy, call it EI, and then the final mechanical energy, called this EF, with no non-conservative work done, this gives This equation is just the fact that energy is conserved. Mechanical energy is conserved. EI is equal to EF. Alright? So we are going to use this principle to successfully solve this problem. Okay, so now that we have established what principle we are going to use, let's go ahead and actually work it out. So let's go term by term. What is our initial kinetic energy? Ki is the kinetic energy at the initial position. And how is kinetic energy defined? We know that kinetic energy is 1/2 m, the mass of the object, times the speed squared. So the initial kinetic energy would involve the mass is a constant both for final and initial points, half is a constant, so it would involve initial velocity or initial speed, and we know that in the initial position the speed was 4.9 meters per second. So initial kinetic energy is then 1/2 times the mass of the child times 4.9 squared. Alright, then let's write down what is our initial potential. So initial potential energy UI is equal to, remind ourselves that U is equal to UG plus US. So UG is the gravitational potential energy and US is the spring potential energy. There is no spring involved in this problem, so this is 0. Only the child is moving in the swing, so it's swinging up and down, meaning that gravity will be present. So we have potential energy due to gravity. So gravitational potential energy is defined to be mass times acceleration due to gravity, g, times the height or the y position. Then in the initial situation here, y is actually 0 because we set our coordinate system such that it is 0 when the child is at the lowest point of her swing. So initially this height is 0. Height is just how far you are off from the lowest level. So at the lowest level you're not far off, you're not any far away from the lowest level, so this is 0. Alright, now let's move on to the final or the right side of the equation. What is K final? It is 1/2 m speed square at the highest point. So at the highest point we know from kinematics or projectile motion that at the highest point, before coming back down, objects go to instantaneous rest. So the speed at the final point is 0. At the highest point is 0. So kinetic energy final is 0. What is the potential energy in the final? Well, potential energy would be maximum because the child reaches a maximum final point, right? So you are farthest away from the lowest point of the swing. So the potential energy would be m times g times the maximum height. So since this is maximum, the potential energy would be maximum. Then let's write down our mechanical energy conservation fully. Okay, so we knew that Ki plus Ui equals to Kf plus UF. We have calculated all of these. Let's put it down. 1/2 m times 4.9 squared. This is 0, so no need to write it down. This is 0, no need to write it down. And final potential is m times g times h. Now we see that each term on both sides of this equation has this same mass in it, the mass of the child, so we can divide it out. And then we can solve for this h by dividing both sides by both sides by g. So if you divide both sides by g, what happens? G here, the g on this side goes away, so you're left with h on one side, h equal to 1/2 times 4.9 squared divided by this g, which is just 9.8. This comes out to be 1.3 or 1.2 meters. Okay, this is the maximum height the child reaches from her initial swing position.